Just talking about a little bit about the science again. So in your blood viscosity research, what exactly changed when participants were grounded?
So what really changed and changed actually the blood viscosity is the electric charge on the red blood cells. Well, so what we found is that by grounding people, the red blood cells become negatively charged, much more than they are normal, and they are when people are not grounded. I'm not saying normally. I retract that word because the normal is to be grounded, but today we reverse that. But
yeah, it's a new normal.
yeah, so because they have this increased charge, which are electrons, like more electrons, they repel each other now. And they are distributed into the blood and not clumped together like they are in most people because they don't have enough charge. You see, I don't know if I should go in there, but you'll stop me if I'm going too technical. But you see, blood is a liquid with floating particles in there, okay? And just like milk, for example, or to give you an example. And these particles floats inside because there is an electric charge inside, like the milk, for example. If you put an acid into milk, okay, it's a colloidal solution. So colloidal solutions are solutions with particles that are transported inside. The milk is the same. If you put acid into milk, you will see that there will be a formation of, a coagulation of some particle and some things, and that is what later will become cheese or become, some people use that. And so there's a whole field called rheology where they manipulate the particles inside, fluids. Like, for example, sewer, the cities have a big system that is based on this knowledge to control and get rid of all the bad stuff in the water. But the blood is the same. It needs to have electric charge on the red blood cells so that they repel each other. And the blood is more like Dr. Sinatra said, more like wine, not like, like ketchup. And that has implication to the entire cardiovascular system. But imagine that your heart has to push through the system something at the consistency of ketchup. It's going to tire. You're going to have your heart problems, heart attacks, and all kind of things like that. But so it's very important to have a blood that has very thin, so that the heart can pump really easily, the blood through the body.
Yeah, and for those avid listeners of the podcast, just to summarize that, we often talk about blood viscosity and the thick clumpiness of the blood, which you've just been describing. When you apply a PEMF device, you can see the cells under a dark field microscope separating. That gives you thinner blood. It's able to carry more oxygen. It's better for reducing inflammation, that sort of thing. So these are the similar effects that were happening with grounding and that you were seeing in your research. But there's something else that we found when we're researching for this episode called Zeta potential. Can you kind of just in simple terms explain what that is?
The Zeta potential?
That's the one.
Okay, the Zeta potential is actually see, when you have charge accumulating some place, you have also a potential that is built up, in an electric potential. Like, for example, in our home, well, at least in America, I think in England is different, but the electric potential is 120 volts. That's kind of like the energy that there is in there. Okay. I think it's 240 volts in England, isn't it?
Yeah.
So similarly, the zeta potential is in volt also, is a measure of how much energy that the cell, electrical energy that the cell has. So the more electrons, the more, of course, electrical energy. And the zeta potential then is a way that is used in rheology to measure objectively and easily how much charge there is. So it's not, I cannot go, and I don't have like small electrodes going right there and measure one blood cell and say how much charge there is on there. I can't do that.
Mm-hmm.
But I can put an electric field and see how the red blood cell move in the electric field, and from that I can deduct how much electrons are on the cells. That's what I did in one of the paper.
Mm-hmm.
Okay, and there's an equation that has been developed by researchers for that. So I can measure the zeta potential, but I cannot go and say, okay, you see how small the red blood cells are. It's impossible. So that's one way to measure indirectly the electric charge on the red blood cells.